Safety glasses. My funky glasses are not here. I'll have to wear these today. Brought out the demo we had here the other day just to see if it would work today. And nobody sees my funky. They must be in my office. Okay, well, brought this back out so we can see if this works. And just want to verify that we are indeed at room temperature. Yeah, room temp. Okay. No, I have not met some of you students. I'm going to try to get in lab today, but if I don't, I do need to learn the rest of you, and I suppose I'll learn the rest of your names. Exam time is when I typically do that. So anybody remember now how I set this up in the class the other day?
Yeah, gas in there is water vapor.
Right, the gas in here is water vapor, and how did I wind up getting water vapor in there? Boiled it for a long time, right? And then made sure that we drove out all of the air, and then we sealed it up and let it cool. So we're sitting here at room temp. I haven't touched this since we left class on Thursday last week. Oh, what? Was this just Tuesday? Okay, so I haven't touched it since then. But we'll see now if we can get this to boil. And I'm just going to set this aside, and Manny, just be prepared in case it jumps up, and I'm going to hold on to this here today. Alright, and we can see here that we can still boil this today. And remember how this works. What's the cause for this? Vapor pressure is equal to the atmospheric pressure. And by pouring the ice water over the top, what are we doing to this atmospheric pressure up here?
Reducing it.
Reducing it, exactly. And once we reduce it down enough, and why is it reducing?
So reducing because the water vapor is liquefying.
Right, the water vapor is going back here into the liquid phase, and it looks like this is just wax on here, so I should be able to get that little bubble off. All right, so just as far as some things coming up in here, we do have an exam coming up next week. That exam is on Thursday, and so what I like to do here is I like to pass around a sheet, which if you have a special seating request, you can put your name on there. If you're fine being arranged by however I would like to arrange you, which is usually alphabetical, A to Z, that's the way I'll go. But if you are like a lefty and you just don't want to be near a righty, let me know. If you don't want an aisle seat or something, let me know. If you want to be in the back corner, let me know. But the only requests I don't honor are ones that where you request to sit next to a specific person. So just let me know if you have a special seating request. If you don't, just pass it through. Once it gets to the back, then send it back up to the front again. Okay, well today what we're going to do is we are going to look at crystal structure a bit more, and we're going to do some unit cell calculations. And unit cell calculations were something when I was a student, for some reason, just totally stumped me. There was a couple areas in chemistry that back in my freshman year that were difficult. One was unit cell calculations like we're going to do today, and the other stuff was buffer solutions, which we hit when we get into acid-base chemistry in about chapter 15 or 16. So if you have any trouble with this stuff here today, just let me know. I think I've got a strategy that kind of helps students with it, but if you don't get it, let me know and we'll see if we can help you out. So, unit cell calculations. We are going to look at page 474, number 56. And when we do unit cell calculations, here are some things that we need to know. And basically we're looking at 5 different values. They are the density, Avogadro's number, molar mass, the unit cell type, and then the volume of the unit cell.
Is this in chapter?
This is chapter 11. The same stuff we were doing the other day. So now if you consider these 5 different items, in order to find the 5th one, you need to know 4 of them. So it might be where you're asked to find the density. If you're asked to find the density, then you need to know these other 4 values. If you're asked to find the molar mass, then you need to know the other 4 values. So again, in order to arrive at them, kind of break them down into these 5 different categories, and you should be able to answer each one. Now, as far as the unit cell goes, this here is going to come from your edge length or the radius. And you recall that in your text we had some equations that we looked at the other day, and those equations, let's see if we can find the table. I think that was on about page 458 or 457, and I must be going the wrong direction here. We'll try to go back to 458. Here we are. And so we scroll down here. Here we go. And so if we happen to know the edge length, great, we're in business. If we don't know the edge length, but we happen to know the atomic radius, then we can take that atomic radius and from it calculate the edge length of the cell. And of course, we're dealing only with cubic crystal structures here. So if we know the edge length, how do we find the volume of a cube? But if it's a cube, it's simply going to be the edge length cubed, right? It's going to be the edge length cubed is what it'll be. So it should be a relatively straightforward type of calculation. As far as the unit cell type goes, you'll need to know whether it's simple cubic, bodied centered cubic, or face centered cubic. And what this will tell us is the number of atoms per unit cell. So you may recall, and I think this is back probably summarized on the same page here. It is. We looked at the number of atoms per unit cell, and we talked about how we calculate those the other day. In a simple cubic, it's 1 atom per unit cell. Bodied centered cubic, it's 2 atoms per unit cell. And if it's a face centered cubic, it's going to be 4 atoms per unit cell. So those are, again, the pieces that we kind of need to fit together. And if we know any 4 of them, we should be able to calculate the 5th of any of these that are up here. So with that in mind, on page 474, number 76, we have a problem, and the problem is worded something like this. All right, here we go. We have palladium. Oh, see, now we didn't memorize that symbol, did we? Palladium. Anybody know the palladium?
PD.
PD, yes. So number 46. So right away we look at number 46, and what should we be able to tell if it's palladium?
Molar mass.
Molar mass, which is going to be 106.42. So we know the molar mass is 106.42. Units are per mole, grams per mole. Exactly. So we have some palladium that crystallizes with a face-centered cubic structure. All right, we got this one, which tells us there are 4 atoms per what? Per unit cell. Okay, then it has a wow, see, they just give it 1, 2, 3. It has a density of 12.0 grams per cubic centimeter. So go right up here at 12.0 grams per cubic centimeter. And a radius of 138 picometers. Well, and that does tell us the molar mass. That's kind of cheating. We should be able to look that up. But it tells us that the radius is 138 picometers. And then the question is, use this information to estimate Avogadro's number. So we want to know, what is Avogadro's number? Of course, we can guess in advance what it should be. We should expect an answer of about? Right, that's what we should expect. And of course, units on here are going to be atoms per mole. Right. So we're going to calculate it, but we're going to see if our data does in fact support this type of answer. So with this in mind then, one of the things we should do is we need to realize that we have units here that vary. We have one length measured in picometers, another measured in centimeters, and so we're either going to have to convert picometers over to centimeters or centimeters over to picometers. And we'll just kind of start off with some way, when we do this calculation, that in the end we're trying to find the number of atoms per mole. So I'm going to set this up out here, where we're going to look for atoms per mole in our answer. Okay. So one of the ways I'd probably start with this one is I'd kind of look to see if I'm trying to get to this out in the answer, I want to start with something that's going to put the correct units in the numerator. And the one that's going to put the correct units in the numerator is the 4 atoms per unit cell. So that's how I'm going to start this calculation. We're going to say that there are 4 atoms per unit cell. I'm actually going to slide that down because I bet I need to calculate a volume. So I'll put that down about right here. Yeah, I'm still saving myself plenty of space. I think we're good. Okay, so next up, let's see, unit cell. Looks like I probably am going to have to find that volume. So to find that volume, I now know what that radius is. I'm going to take this radius and I'm going to calculate that volume of the unit cell. Remembering that volume is equal to L cubed. And then if it's a, what is this, face-centered cubic? If it's a face-centered cubic, we go back to our table here, which tells us, and by the way, I don't expect that you memorize these conversions of edge length unless it's a specific derivation you're asked to do on an exam, which is possible that you could be asked to do that. But we're dealing with a face-centered cubic, which is 2 times the square root of 2 r. So we'll come back here and tells us we have 2 times the square root of 2 r is equal to the edge length. Well, we know what the radius is. We can go ahead and substitute that in. That's 138 picometers. And that will give us the edge length. We calculate this out. 2 times 2 raised to the 0.5 power times 138 is going to give us an edge length of about 390.3. I always like to carry along an extra digit. If we were to round this later, though, how many significant figures should it have? 3. Okay, but Again, to avoid rounding errors, I like to keep extra digits in the calculation. So now if this is the edge length, we should then be able to find the volume. The volume again is L cubed. So we're going to take the 390.3 picometers and we're going to cube that. So basically whatever answer we have on the display, we'll cube it. Looks like I wind up with a nice big number here. And I'm going to carry with an extra digit, so we'll have 5.947 it looks like, times 10 to the, and can anybody see how many decimal places that is? 7. Yeah, so we're confirming that. I get 7 as well. What would the units on here be? Picometers cubed, right. So what we're going to do with this now, this is the volume of the unit cell. So we could say that there's this many picometers per unit cell. And not this many picometers, there's this many cubic picometers per unit cell. So what that would enable us to do is to pop this in here as a conversion factor. Where would unit cells go? On the top, and on the bottom we'd put in 5.947 times 10 to the 7th cubic picometers. Unit cell cancels out. So now, from here we have the number of atoms per cubic picometer. And we need a cubed unit here, which we have. It's cubic centimeters. So what we should probably do with this cubic picometers is to convert it to? Right, to centimeters. Now, this is where we need to think back to our conversions. The conversions that we'd have here, I'm kind of running out of room. Here we go. For every 1 meter, we have how many picometers? For every 1 meter, we have how many centimeters? This one's 100, which I'm going to write as 10 to the 2nd. The prefix pico means 10 to the negative 12. So that means we need 10 to the positive 12 picometers for every 1 meter. Now, I don't remember if I mentioned this, but I always do it in my intro classes because even after I got to your stage as a student, I sometimes got my powers mixed up. And here's the way I always remember things when it comes to powers of 10 and conversions. I can think in my head, and do that very well, knowing that if there's a meter or a picometer, I know right away which one's the bigger unit. And the bigger one is going to be the meter. So if the meter is the bigger unit, it's going to be associated with a number that is smaller. And it always works that way. If you never know where to go with your conversions, remember that the smaller number always goes with the larger unit, the larger number always goes with the smaller unit. And you'll never ever get it wrong. And it works with every type of conversion you'll do, not just these metric to metric ones. So we take the big number there and associate it with the small unit of picometers. And then what we do, since these two are equal to each other, we can then say that there's 10 to the 12th picometers for every 10 to the 2nd centimeters. And we can then use that as a conversion because those two are equal. So to do this as a conversion, on the top we'd put in 10 to the 12th picometers. Down on the bottom we'd put in 10 to the 2nd centimeters. Now what we could do is repeat this conversion 3 different times, or we could take this conversion and cube it. And of course that cancels out the cubic picometers. Doesn't cancel out the, the cube on the parentheses, because the cube here still has to apply to all of the other values that are in here. But now that's going to give us units of cubic centimeters on the bottom. At this point then, we have 12.0 grams per cubic centimeter. Where's the 12.0 going to go? on the bottom. So it's going to be 12.0 grams per every cubic centimeter on the top. Cubic centimeters are going to cancel out, but again the cube doesn't, because that still has to be applied to the other quantities in parentheses. And at this point, if we stopped, we'd have the number of atoms per gram, but we want to have the number of atoms per mole, so that means we need one more conversion here, and that conversion is going to be not Avogadro's number, the molar mass. There's 106.42 grams per mole. So where's the 106.42 going to go, top or bottom? Right. So we have the 106.42 grams per mole, and that enables us to cancel out units of grams. And so in the end here we have units of atoms per mole, which is what we had hoped we would wind up with for the units. So now we need to multiply this through, and on your calculators, this is where I often see some errors, and you can do this a number of different ways if you wish. I have a number of students in the past that have just been unable to do this type of calculation on their calculators. So we can kind of help this out here, because 10 to the 12th over 10 to the 2nd is going to be equal to 10 to the 10th. And 10 to the 10th cubed is going to be 10 to the 30th. Okay? So 10 to the 10th cubed is going to be 10 to the 30th. And if you don't remember that, that's unfortunate, but it's expected that you know how to do that. But then, if you enter that into your calculator, you need to remember how to do that the right way. And if you use your scientific notation button, that is entered into your calculator by hitting 1 EE 30. Because that EE button stands for times 10 raised to a power. And usually, and this is the first time I've taught it, so maybe you guys are a lot smarter than I'm giving you credit for. But the biggest mistake I often see on this is when we get back into a new semester like this, students will put in 1 times EE 30. And what that's going to do is it's going to take it 1 times 10 times 10 to the 30th type of thing. So I want to make sure that this is all we enter in when we enter in 1 times 10 to the 30th. And the other place where I often see mistakes is that I'll see students actually put in, well, I guess you could have put in 10 raised to the 30th, but I sometimes see students use the 10 to the X button. The 10 to the X button is not for scientific notation. That one is for anti-logs. So if you get in the habit of using that 10 to the X button, very often I see mistakes with it. You should get used to using your scientific notation button, which is that EE function. So if we multiply this through, we'll take 4 and we'll divide it by 5.947 E7. Then we're going to multiply it by 1 E30. We'll divide it by 12, and then we'll multiply it by 106.42. And when we do this now, how many significant figures should be in that answer? Not 4 or 5. It's going to be 3, because we had 3 right here. That gets propagated through to the volume to right here. So that then would be 3 significant figures. And so out of 3 significant figures, I'm seeing an answer of 5.96 times 10 to the power of 23. And that's atoms per mole. So how good did we do? How well did we do with our approximation? Pretty darn good. Because Avogadro's number, of course, we would expect an answer of 6.02 times 10 to the 23rd. So any questions on this calculation for this problem? All right. So remember, then when you do these types of calculations, you go home or whatever, come to exam, think of these 5 different items. whichever one you are trying to calculate, you need to know the other four, and you should be able to obtain that information quite readily. All right, we're going to wrap up Chapter 11 by looking at crystal structures. And there's a figure here on page 463 that talks about crystal structures. And want to be clear here, first of all, before we talk about crystalline solids, which is what this figure pertains to, and this is the last section in Chapter 11. Crystalline solids aren't the only types of solids. Solids may be crystalline. When we talk about them being crystalline, that means that the atoms or ions or molecules, whatever they are organized into some pattern like we already talked about. They're either organized into something that's a cubic structure or something that's a hexagonal structure. There's about 20 different types that they could organize into, but it's a very organized pattern that repeats itself, and those are called crystalline solids. But there's another type of solid, and I looked through very briefly in your text, I didn't see it, but the other broad class of solids, anybody know what that other broad class is? Amorphous. It's amorphous solids. And amorphous solids, these here do not have an organized crystal structure. Rather, the molecules or particles, whatever that makes up an amorphous solid, is less organized. It still has the characteristics of solids. For example, glass is a type of amorphous solid, but the particles that make up the glass are not in a very organized pattern. And when they're not very organized, a couple things happen. One of them is that they sometimes can flow over long periods of time. Because they aren't organized, they don't have those intermolecular forces that are going to hold them into place. You could have something that flows over time. Let's say that, well, butter would be another example of well, that's more of a mixture, but butter would be like another example. If it sits there longer, it's going to wind up being a little fatter on the bottom than it is up near the top. Yes?
Really old stained glass.
Really old stained glass will do what?
It will flow, form ripples.
Yes, it forms ripples in it. And part of that just has to do with how that solid or amorphous glass and winds up flowing over long, usually very long periods of time in there. So
in that sense, would that be like a really, really viscous liquid?
Exactly. And the other characteristic that amorphous solids have is that they do not have a well-defined melting point. They tend to melt over a broad range of temperatures. And if you took your Chem 1061 here, you may remember one of the labs that you did in the first semester, you made your own pipettes. Remember melting the glass there and drawing it out? Well, it didn't melt immediately from a solid into a liquid. It softened up, and so that's yet another characteristic of amorphous solids, is that they have a very broad, very wide melting range. And so you talk about them softening over a temperature range rather than liquefying. There's not a defined melting point or freezing point when they do that. And so amorphous solids are somewhat cheated here in your text. And your text focuses more, as do chemists for the most part, when we deal with this, we take the harder and more difficult topics of amorphous solids and put them in more advanced classes. But on page 463 then it talks about crystalline solids and how they're organized, and we'll just talk about them very briefly. We'll start with the molecular solids. As mentioned here, molecular solids means that they're made out of molecules. The smallest unit there is a molecule. So we have something like water, for example. These would be the smallest units of solid water. They would organize themselves, as remember that an oxygen of one molecule is always going to be near a hydrogen atom of a different water molecule. And so the smallest units in a molecular solid will simply be the molecules. Then we have ionic solids. And I believe we had this one out here the other day. This is a model of, remember what this is? Salt. This is sodium chloride. And so in an ionic solid, you also have the organized pattern, and in the case of sodium chloride, we actually don't have molecules of sodium chloride. We refer to them as formula units, and in something like sodium chloride, we would count them and we'd see that the ratio of sodium to chlorine atoms is a ratio of 1 to 1. If we had something like calcium chloride, which is CaCl2, then we'd see a crystal structure that has 2 chloride ions for every 1 calcium ion. Characteristic of these, just like we passed out the salt the other day, which I have right here. When we pass this around, we saw those cubic crystals in there. They also have relatively high melting points. If you ever tried to put some salt in a fire and melt it or burn it, you can't do it. You need to have something very hot to get an ionic solid to melt. Then on the atomic solids, we have 3 different kinds here. We have what we call non-bonding solids. These here are comprised of individual atoms that are held by dispersion forces. These would be basically most of the non-metals that are in your periodic table, like fluorine. Fluorine wouldn't be it, because fluorine is going to be molecular. It's actually F2. So it would probably look more like it's something like the noble gases, which would be argon and krypton and so forth. And they're going to have melting points that are really low. Your metallic ones, these of course would be all metals. These melting points are going to be varied. The way that we describe a metal is we say that its metals consist of positive ions sitting in a sea of electrons. So I'll just think of it as a big ocean or sea of electrons, and those metal ions are in the middle of all those. And then the last one is a network covalent solid, and these here are held together by covalent bonds, and one characteristic of these is that they're going to have very high melting points. And part of the reason why they have high melting points, and I brought out an example. Now, anybody know what this is a model of if I kept building this out? This is diamond, exactly. This is diamond. And if you were to actually take this structure here and try to actually make or move it or break it or whatever, you'll see that this is going to be a very sturdy, very durable structure. And that's because it has this network of bonds that is in all 3 dimensions that winds up holding this together. And so diamond is an example. If you are into tools, you might have like carbide tipped tools, like silicon carbide is an example. It's used for cutting things, and they're used for cutting because they are just like diamond. Diamond can scratch glass. These carbide tools, like silicon carbide and so forth, have the same network, except in silicon carbide, every other atom would be a silicon atom. But because it's in group 14 of the periodic table, just like silicon, and those silicon atoms take up a little bit more space, you can wind up producing those tools again that are very durable, because the ability to break off these bonds winds up being very difficult in those solids. So that kind of takes us through everything here for Chapter 11. Are there any questions that you have on anything in Chapter 11? Yes, sir.
Just with diamond.
Yes.
On the edges of a diamond molecule.
Yes.
Will the carbon try to bond to things like oxygen or hydrogen, or will it double bond?
It probably would be more double bond. That's actually a good question. I don't know for sure, but something like diamond is super chemically inert. So it must have something where those bonds have folded back on themselves, and they are able to bond with other things. Yes, sir.
Can diamond be eaten away by acid?
I don't know if it would. It would only be the strongest of acids, like probably like what's called aqua regia, which is a mixture of sulfuric and hydrochloric acid. But I would think it's pretty impervious to just about anything. So my inclination would be no, it can't. Now I have actually seen diamond react before, and I would love to demonstrate it. I can't. But where I've seen it react before is heat up a diamond really, really hot, and then you drop it into some liquid oxygen. And when you drop the diamond into liquid oxygen, then you will see a reaction forming some carbon dioxide when that happens. And it's actually pretty freaking amazing because it gives off this super white glow when it does so. But I don't have diamonds to burn, so. And I don't have a bunch of liquid oxygen laying around either. I can make a little bit, and I do. And maybe your teacher made liquid oxygen in 1061, but I can make liquid oxygen by taking balloons filled with oxygen and then cooling them in liquid nitrogen. So, anybody else with questions? All right. Well, we'll put this away, and then what we're going to move on to is solutions. And when we start with solutions, I have a number of terms here that you don't need to write all these down. If you know them, don't write them down. It's not smart to write them all down if you already know them, right? But let's look at the list here and just see if there's anything column 1 that anybody needs help with. There usually is. Which one you got in your mind there, Donovan?
Miscible and immiscible.
All right.
I got an idea, but
What is your idea? What does it sound like?
it sounds
If something is miscible, what does that sound like might happen?
immiscible. Yeah, I want to play this game.
Yeah. Well, we could probably guess that they're opposite of each other, right?
Well, right.
All right, we got that much. See, that's good. That's a good start. So as long as you know one of them, and here's the easy way that I remember these, miscible sounds like mixable. And that's exactly what they are. And these two terms apply to fluids. If we say that we have fluids that are miscible with each other, that means we can mix them together in any proportion. And by fluids, we're talking about either liquids or gases. So gases are fluids, liquids are fluids.
So, oil and water are immiscible.
Oil and water would be immiscible, exactly. What would be two liquids that are miscible? Water and... Oh, come on. It's Thursday. It's a new Friday, right? What a lot of people do on the weekends.
Vodka and orange juice.
There you go. Alcohol and water. I don't do that one, but alcohol and water are miscible with each other. You can mix them together in any proportion. Good. All right. Now, when we talk about gaseous, liquid, and solid solutions, many of us have in our mind that solutions only come in the liquid phase, but they don't. Solutions can come in any phase. When chemists use the word solution, we mean any type of homogeneous mixture. And so that means that down on the molecular level, or the atomic level, whichever we want to talk about, that means that the particles are intimately mixed and intermingled with each other. They take a sample out of there. We can't tell that it's actually a mixture of the two. And I have some solutions that are up here. In fact, as you look at this solution, how many substances does it look like is in here? Just one. Turns out that there's a couple different substances in here. But they could have a final state of being a gas, liquid, or solid. So what would be an example of a gaseous solution?
Air.
Air. Easiest example. How about a liquid solution? Yeah, I got one right here. Rubbing alcohol is another one, which is isopropyl alcohol in water. Solid solution? Salt is not. Salt is a compound. Salt's a compound. This stuff here probably is. Many of you have one in your mouth. If you have a dental amalgam, what is an amalgam? It's a filling, right? And if you have an amalgam, do you know actually what probably, I don't remember if it's the most abundant element or second most abundant element in your amalgams? You know what you're carrying around in your mouth if you have an amalgam?
Aluminum?
Yeah.
Mercury?
Mercury. Yeah, mercury. It's about 40% mercury, a dental amalgam. And so that's actually one of the things that makes it so pliable. And so it's ground up into super, super fine powder, and that allows it to be packed. Yes?
Isn't mercury toxic?
It is toxic, yes. But what's most toxic about mercury is not so much the liquid or the solid form of it, it's actually the vapor, the gaseous form. And so whenever we have mercury, which we don't have, I'm trying to think if we even have any around here anymore, but when we did, we would always be concerned about finding wherever the heck that mercury is. Because what would happen, just like any liquid, all liquids have a vapor pressure. And if they have a vapor pressure, that means that they are constantly evaporating and turning from a liquid into a gas. And so then when we inhale that vapor, we're inhaling basically individual atoms. And those atoms then can wind up ionizing. And it's the ionic form that causes the problem. So the metallic form doesn't. It's the ionic form that does. And it's usually then when we wind up inhaling it, or like if we consume fish that has mercury in it, for example, where it's spread out and then you have your enzymes and your acids in your stomach that digest them and ionize them. So that's the biggest concern with them. Okay? So yeah, dental amalgams. It's primarily mercury. Brass is a mixture of copper and tin and whatever else. So again, if you have a metal alloy of some sort, that's a solid solution. Let's go down the second column. Any questions coming down the second column? Yes, sir.
The difference between concentrated and saturated.
Oh, good. Glad you brought that up. Because very often they're confused with each other and they're not. Basically, if we talk about the difference between these two, dilute and concentrated, dilute is something that has a relatively small amount of solute. Right. If it's dilute, a relatively small amount of solute. And if it's concentrated, it has a relatively large amount of solute. So if we made a concentrated salt solution would have how much salt in it? Lots. Okay, so we're just using relative terms, we would just say lots. That'd be a bunch.
Very scientific.
Yes, it is. Well, see, that's the way I learned stuff. I grew up on a farm. So it's just a lot or a little, right? So if it's concentrated, lots of stuff. Lots of solute, that is. Compare that to saturated. And a saturated solution is a solution which has dissolved in it. In fact, we're going to look at these, and we might as well just start with saturated right now. And where can I put these terms? I think we'll put it on the next one. We'd say that a saturated solution is a solution that has dissolved the maximum amount of solute in a given amount of solvent at a specified temperature. And there's three variables that are in here. If we look at it, it is the amount of solute, the amount of solvent, and the temperature. So it's actually a three variable definition. And of course that's the topic of your lab this week. When you generated that solubility curve, or those of you that are going to be in lab later today, when you generate that solubility curve indicates the saturation point. Okay, that's a saturation point. And if we have an unsaturated solution, this is one that contains less solute. we should say contains less dissolved solute than a saturated solution at the same temperature. And we could then have a super saturated solution. I still haven't answered your question yet. I should have done that already, but we'll do this first. So, super saturated solution. And this is one that contains more dissolved solute than a saturated solution. At the same temperature. So the question was then, what is the difference between concentrated and saturated? Well, the difference is that a concentrated and dilute, those are relative terms. You could either have a whole bunch of solute dissolved or very little. When it's saturated, we might have some graphs that look something like this here. And this is a bunch of solubility curves. And if we look at the units on these solubility curves, we see that it is a plot of the amount of solute per specified amount of solvent at various temperatures. And so we could have something like sulfur dioxide, which in this case here at 60 degrees Celsius maybe only dissolves about 4 grams of SO2 per 100 grams of water. But we could then have at 60 degrees Celsius something like sodium nitrate, which would dissolve 124 grams, and it would be saturated. So it depends upon what the substance is. And in some cases, a very, very tiny amount can only dissolve, and that's all that will ever dissolve. In other cases, a very large amount can dissolve at the same temperature. Okay? So they will vary. Still a question?
So that's talking about saturated, or saturation basically.
Right.
Just explain.
Each of these lines represents a saturated solution, exactly.
And
Yeah.
then concentration is just talking about when it's not specified.
Concentration would, well, there you're actually specifying a concentration, but you could have a very concentrated salt solution that isn't saturated. So for example, if I took some water and I dumped a bunch of salt in it, maybe 25 grams for every 100 grams of water, that's going to be really, really salty stuff. But it's still not saturated because it could still hold more. Okay? So it's going to be very concentrated, but because it can still dissolve more.
Oh, I see what you're saying. Okay.
Contrast that with something like, this is why I carry things around on my cart. Contrast with something like this, which is chalk. How much chalk do you think I can dissolve into water? Very, very little. In fact, if we had a plot of calcium carbonate in water, this plot would be somewhere like right down here. You wouldn't even be able to see it because I can only dissolve like about maybe 0.03 or 0.04 grams of calcium carbonate for every 100 grams of water. And I'm trying to think, yeah, that's something we cover in this semester. It's about chapter 16 or 17 where we calculate some solubilities.
Just simply put, you can put a lot of chalk in water and that's concentrated, but
I can't put a lot of chalk in there because again, when we talk about it, it's got to be dissolved.
oh, I see. Okay.
Yeah. So in order for us to make a solution, it's got to be dissolved, and you're not going to dissolve a lot of chalk in the water. It's going to be very, very, very little, like about 0.0. I am making up a number off the top of my head, but I know I'm in the ballpark. Okay, it's like a 0.03 or 0.04 grams out of every 100 grams of water. It's a very, very tiny amount. Question?
I was going to say that I've always thought saturated was when it gets to the limit where if you add something, it's not going to take it no more. It's going to...
That is true.
Solid and stuff all in here. concentrated can still take a little bit more, depending on how concentrated.
Exactly. Concentrated is, when you use the term concentrated, it has really nothing to do with saturated, because in the case of chalk, remember, a very, very, very tiny amount of chalk can dissolve in water. But yet, we would say that type of solution is dilute because such a tiny amount would be in there, but yet it would still wind up being a saturated solution if it's achieved that maximum amount. So, concentrated and dilute are relative terms. Saturated is a very defined term. It's based on these solubility curves, and if it's right on the line, that describes a saturated solution. So we do need to specify the three variables. So if we did something, let's say we looked at something like potassium nitrate, we wanted to talk about its solubility. Let's say we want to talk about its solubility at, trying to pick an easy one, 20 degrees Celsius. We'd say the solubility of KNO3, we could say at 20 degrees Celsius, so we find it right here, 20 degrees Celsius, looks like it's about right here, which would be about how much?
32.
About 32. So we could say there'd be 32 grams of KNO3 per 100 grams of water, and then what else would we have to say? Right, we'd have to say the temperature at 20 degrees Celsius. And then we could talk about it at, say, 60 degrees Celsius. That's a nice round one here. We could then say it's 110 grams of KNO3 per 100 grams of H2O at 60 degrees Celsius. So when we specify solubilities, we have to specify all three variables when we do it. Two variables won't work. Okay, anybody else? Oh, we got to do some demos, right? Because without demos, it just doesn't mean anything. So let's look at some salt solutions, and we'll test out what you asked about here. And both of these are solutions of salt. Okay? And of course, if you look at these, I don't know if you can tell, but compare, they really look pretty much the same. Okay? But what I'm going to do now is I'm going to put some salt into each one of these. And I never measure, but we'll kind of go about that much. We'll try to put about that much in here too. And then what we're going to do is we're going to shake these up and see what happens. And I always trust what I grab off the shelf, and hopefully that trust works today. It kind of does. Now, do you see what happened in this one? Dissolved. So that means that this must have been a what type of solution?
Unsaturated.
Unsaturated. This one did not dissolve, so this must have been, it must have been what? Saturated. This must have been a saturated solution. And what is it now?
Supersaturated.
It is not supersaturated. It is still a saturated solution, because in order for it to be supersaturated, this stuff would have to be dissolved, and it did not dissolve. So this solution is still a saturated solution. So let me say, yes?
How can you turn a solution from a saturated to a supersaturated at the same temperature? You can't.
You can't do it. Right, as long as the temperature is constant, you cannot make a supersaturated solution. So what do we have to do to make a supersaturated solution?
Heat it up.
You have to heat it up, exactly. And once you heat it up, then you would dissolve in more stuff. And once you dissolve in more stuff, then you can cool it back down to room temperature. If it stays in there, then that solution is going to be a supersaturated solution, yes.
What about instead of changing temperature, changing pressure?
What's that?
Could changing pressure affect that?
Yes, but it will not affect solids. It would affect
Liquids.
not liquids?
Gases.
Gases, right. And so that's exactly what happens in, nobody has soda out here today? Okay, well that's exactly what happens in soda. Basically, you put it under pressure, it's all in solution. As soon as you remove the cap from there, what happens when you remove the cap? You hear the fizz? All right. At that point, the solution has become supersaturated with carbon dioxide. Of course, it's not stable there, so the longer you let that bottle or can stay open, what's going to happen to the CO2? It's going to continue escaping from that solution because it's supersaturated with CO2. Question?
But for gases, you'd have to cool it down to make it supersaturated?
Yeah, that's kind of the interesting thing here. Note these things. Oh, you looked at it. I was going to ask you which one it is. I forgot the key is right on here. Notice the general trend. When you increase the temperature of solids, what happens to the solubility? Solubilities go up. And when you increase the temperature of gases, what happens to their solubilities? They go down. Very simple explanation for that. And you need to know it. So I'm glad you asked. Why would solids increase their solubility as the temp goes up? Why would solids increase their solubility when the temperature goes up? Very simple. What happens to kinetic energy when you increase the temperature? It goes up. So molecules, whether they're molecules or ions, whatever's in there, those particles, if you increase the temperature, they're going to become more active. The way they can become more active is by going into a dissolve phase rather than staying in the solid phase. So they can show off their kinetic energy by moving around more. But we use the same argument when we talk about gases. If we have gases that are dissolved in water and we heat up, or actually in any solvent, but if we heat it up then the gases are going to start escaping. And why would the solubility then go down as you heat a gas or heat a liquid that contains a dissolved gas? Same argument. If we increase the temperature, what happens to kinetic energy? And it goes up. And if if gases are dissolved in the liquid, that's confining them. They can't be as mobile. So the way they're going to get more mobile is to escape out into the gaseous phase. And so that's basically the explanation that we use to describe the difference in solubilities between them. Now again, it's a general rule because they don't all work that way. For example, if you look at sodium sulfate, you'll see that sodium sulfate, being a solid, actually decreases its solubility with an increase in temperature. There are some exceptions to the general rule, and it has to do more with some stuff. I think we'll get into it later on this semester when we talk about entropy. We have competing effects of entropy and enthalpy that wind up determining whether something dissolves or not. And if you don't know what entropy is yet, you will at the end of the semester. Okay, so any questions on these? Okay, a couple cool things. First, I want to get back. No, we'll do this thing first because this one's funner. Okay, so I have a couple of solutions here. Actually, I got 3 of them. And these are supersaturated solutions of sodium acetate. And what I'm going to do with these is I'm going to take some sodium acetate and try to dissolve it into each of these solutions. And I need the sodium acetate, which is where? I must have taken it out. Here we go. So in order to dissolve this, oh, you got to watch this. This is fun. I think you can see this with this camera on here. Where are we at? Right here? Okay, good. So, see, I can't even see anymore because I got this glasses on, but I think, can you even see the little speck on the, there's one little speck on the end here. All right, I'm going to try to dissolve the sodium acetate into this solution. Is it still on there? I think it is. Yeah, I see it's shining now. All right, so you see we got the liquid sodium acetate here. I'm going to go ahead and put in this one crystal, and nothing's happening. Oh, well, something is happening. There we go. That was kind of weird. And I think this solution is a little bit more concentrated than I wanted. Okay, well, I didn't make this one. Somebody made it for me. There we go. So you can see what happens there. That one wasn't dramatic. We'll try another one. Let's, oh, you know, we should, with this one here, let's go ahead and put in some salt in here. Now remember, this is supersaturated with sodium acetate, and I'm going to add in some sodium chloride. And we should have a couple thermometers here, so just hold on to it. Oh, just the bottom. Room temp? Room close? Room temp? Room temp? Okay. So we're going to go ahead and add in some of this stuff, which is sodium chloride. And we'll see what happens when we add in some sodium chloride. And we'll see that that just sinks to the bottom, doesn't do anything. But if we come back here now and take our sodium acetate, and I'll try to get one crystal again on here. I can't get one crystal. Well, maybe I have to go with like 2 or 3 because I'm just trying to hurry this. Alright, so we'll come back here, and again you see the liquid. Drop in my sodium acetate crystals, and we see how the crystallization in here occurs. This one's much better. So what do you think's happened to the temperature? Gone up or gone down? So you go ahead and pass this around. Don't tell anybody what you're feeling. Just pass them around to the back there. Can you think of a use for that?
Use for that?
Yeah. Can you think of a way we'd use that? Like an everyday?
Hand warmers?
Hand warmers, yeah. That's what I got. So you can try one here, try one there,
Bring the thing.
try one back here, ahead, and try one back here. Alright, now there's a little metal disc in there. Hold it up, click that metal disc, and hold it up so people around you can see, watch what happens. But inside those packets is a supersaturated sodium acetate solution. And what that little metal disc is for, I'll take it. What that metal disc is for is to create a small seed crystal. And as soon as you form a small seed crystal, then what happens is that all of the rest of the seed crystals build up on the sodium and acetate ions that are in solution, and they come out. And that's why when I put in the sodium chloride, notice that it did not precipitate. And that's because sodium chloride has a different crystal structure than sodium acetate. As soon as I dropped in a seed crystal of sodium acetate, then what happened is all of the excess sodium acetate that's in here wound up crystallizing out of solution. And so those things that were passing around, those are packets of supersaturated sodium acetate. And these have been used many times. If I want to reuse these, what do I do to that? Yeah, I just put them in some warm water and get them to redissolve, and then I cool them back down to room temperature, and then I can demonstrate them in my next class. And I can do it over and over and over again. And we contrast those with these types of hand warmers, which I must have brought out somewhere. Here we go. These hand warmers are different than these because while these can be reused, these cannot be. And these here are sealed up in an airtight package because these here contain some iron metal. It's basically ground up iron powder. And then there's a small amount, if you look at the ingredients in here, there's a small amount of salt and some carbon in here. But this is a very simple chemical reaction with these. And these here is basically iron reacts with oxygen in the air to produce iron oxide, commonly known as rust. And that process is exothermic. And so these are the type, when I go skiing, that I like to use because they keep my hands and feet warm for a long time. And if I want to stop the reaction, all I need to do is put them in a container that seals off the oxygen, and that'll stop the reaction. I can take them out again. As soon as they expose them to the oxygen in the air, they wind up reacting once again. But once these are completely reacted, what do you do to them? You throw them away, because once it's all been converted into rust, you can't use these anymore. So any questions on the difference? Yes?
Could you take undo the package in those and take the rust off and repackage them and reuse them?
You could, sure. But you'd have to get the iron back in there, the pure iron. And they're made out of cotton, so they're permeable with oxygen in the air. Yes?
So just remind me here, is this because the sodium acetate thing, is that because the freezing of water is exothermic?
The crystallization, and not just water, but any type of crystallization is typically exothermic. So those of you that are going into lab today will observe some of the stuff that the other half of the class observed yesterday, and you're going to be cooling down solutions of super, I guess it's saturated potassium nitrate. And what will happen is that once it gets to the point of crystallization, the temperature actually drops down and bumps back up, because once the crystallization begins, it gives off heat energy that brings that temperature back up. So any type of crystallization is typically an exothermic process. Okay, anybody else? Now, you've seen supersaturated solutions before. If you've had honey, okay, honey is an example of a supersaturated solution. If you let honey sit on your shelf for a long period of time, what happens to it? It crystallizes. Sure. Now, nobody wants to spread crystallized honey on their bread, right? So what do? Heat it up, and that will redissolve the sugar that's in there. Once it's redissolved, it will typically stay in solution until something triggers it. Usually once the honey begins to crystallize, it happens very rapidly, and the entire thing winds up crystallizing out of solution. My dad was a beekeeper, so I know all that stuff. But another thing that I remember, my first exposure to supersaturated solutions was in elementary school, making rock candy. I don't know if any of you have ever done that, but you basically make a supersaturated sugar solution. You heat it up, you dissolve in a whole bunch of sugar, you cool it back down to room temperature. The solution then is supersaturated, and then what do? You suspend a string in there, and you can put a few crystals of sugar on there, and then the sugar will grow in big rocks around those small crystals. So, fun stuff. Now, with gases, here's kind of a cool thing about gases. Now, oxygen's not on here, but if oxygen was on here, what shape would we expect to see for the graph? Going up or going down? O2. Going down, because oxygen is a gas. Okay? So that means if we go back now, oxygen is in here, and I don't think it gets quite this high, but that means that the greatest solubility of oxygen is going to occur at what temperature? Sits right here at 0 degrees Celsius. And so you may have heard there's some issues like when you put in new developments, you're going to see big fences that go up around those developments for a couple of reasons, especially if they're near like a stream or a river. And that is because, one, you don't want to get a bunch of dirt or silt or whatever in the river, but a second one is something called thermal pollution. Thermal pollution. And thermal pollution is exactly what it says it is. It's not pollution caused by any chemicals, but it's pollution caused by heat. And anybody in here a trout fisher person? Fish trout. Okay, what type of water?
Fresh water.
Fresh water, what kind of temperature? Yeah, very cool water. They like it where it's really, really cool, where it's shaded and so forth. And trout streams are typically spring-fed, which has really cold water coming out. So when you put in a development and we have water that runs off of pavement, like in a thunderstorm. Well, they go into storm sewers, and those storm sewers ultimately empty into rivers or lakes or wherever else. And if they empty into like a trout stream, that isn't good, because when it thunderstorms, usually it occurs in temperatures that are really warm. The pavement then is even warmer because it's been beat down upon by the sun. And that warm water runs into those rivers and creeks and causes the temperature to go up. The temperature goes up, what does that do to the solubility of oxygen? It causes it to go down. If it causes it to go down, then what happens, especially in trout streams, is the trout wind up dying. They can't stand it. And so one of the things that I did when I was a student was I worked on at an electric power plant, and we were to monitor dissolved oxygen levels coming out of the power plant. Now, a power plant, this was down in Sioux City, Iowa. The power plant, it doesn't matter whether it's coal-fired or whether it's a nuclear power plant or whatever, in order to keep a power plant running, you have to have enormous amounts of water. And if you've ever gone up by the power plant up by Monticello or Big Lake, for example, you'll see in the middle of winter that there's all sorts of steam and fog coming off it because there's warm water that's being discharged back in the Mississippi River. So, great in the winter, but in the summer, it's not so good, because what will happen then is that if those dissolved oxygen levels go too low because the water's too warm, then again you start killing off a bunch of fish. So, here's what happened at the power plant where I worked. This is the Missouri River. The power plant sat up here on a hill. Coming out of the power plant was kind of something that looked like this. And the water that came out of here was sent over these cascades. Now, what do you think the idea of having these cascades was for? Yes?
Cooling and bringing in oxygen to the water.
Exactly, it did both of them. By making the particles of water as small as possible, that made it so that they could dissipate their heat more rapidly. The other thing that it did by churning over them is that it allowed it to mix with the oxygen in the air. And so we would often measure the dissolved oxygen coming out here, dissolved oxygen right at the end, and then we would of course measure it further on down the river to see what sort of impact that the power plant had on the river. And it was very important then that that these cascades functioned properly, and that the temperature coming out of here wasn't too high, because again, we didn't want to be killing off all the fish that were there in the river. Now, some of the kind of side benefits of that, have any of you ever been up to Monticello in the middle of winter? Yeah, what do they have there? Swans, trumpeter swans. And they have hundreds and hundreds and hundreds. It's deafening. Like in about January, if you go down there, they'll have, I think I was there with 2,000 trumpeter swans one time. And it's just incredibly loud. But that's not natural either. It's fun to watch, but not very natural either. So anyhow, that was kind of a fun little project that I worked on back when I was a student. So with that, I guess we'll come into next class. We'll do numerical with our calculations on solutions. So that's it.